Hello.
Good morning, sir. Good morning, sir.
Yes.
Is it audible now, sir?
Yes, sir. Yes, sir.
Okay.
Yes.
So, good afternoon, everyone. Welcome to the second day of our workshop on efficient design and manufacturing of printed circuit boards using IPC standards. I would like to invite Karnakaran sir to continue with the session.
Thank you, ma'am. Few seconds. There is some presentation connectivity is missing. Three more seconds. I'll rejoin once again. Sorry for the disturbance. Madam, is it visible now?
Yeah, visible, sir. You can. Okay.
Shall I continue?
Yes, sir. Yes, sir. Welcome.
Okay, thank you, thank you. Okay. So let's start our second day lecture. So at the outset, I sincerely thank the organizer for giving me the opportunity. Now, before we go into today's topic, let us review the previous day's work which we have done. So last class we briefly reviewed what is required for your basic design with reference to IPC standard, and we also just briefed how the IPC evolved and what is historical things behind that. So what is IPC? IPC is nothing but is a code given for PCB design and manufacturing standard, isn't that right? So how the PCB evolved is formed by six companies initially 1956, and there onwards they have enforced a lot of regulations and improvements and so on. And today we are going to have a special IPC standard which is exclusively for designers. Okay, and basically this particular IPC standard gives the printed board geometric tolerances and dimensions and tolerances. So generally this particular topic generally is not dealt in the classroom, so that is why I took this particular topic for the second day. Okay, and basically what we do in our PCB ORCAD design, we do all the schematic design, and we optimize the layout, and we go for printing. Okay, but we will not be worrying about what is the internal dimensions and tolerances stipulated by the consortium or the code. Okay, so today our objective is to know the basics of dimension tolerancing with reference to PCB. And if we go into depth, this particular code or regulation is derived from ASME 14.5 code, which is exclusively for mechanical and production engineers for standardizing the products in products, especially. Okay, so the entire code has been derived from ASME, American Society for Mechanical Engineers, 14.5. Now, before we go into the review of this particular IPC code, let us briefly observe what is happening in the job market also. So I have given two slides to give you glimpses of the requirement where people are require these particular standards, IPC standards also. So one particular advertisement, if you see 3 days ago occurred, lead PCB engineer requirement. And if you observe, most of the topics we see in the classroom is also been there, but especially when we come for standards, you can see they are very clearly mentioned. You should have a familiarity with IPC triple two guidelines. Okay, so this particular guideline generally has not been dealt elaborately in the classroom. So that is why we enforce these particular regulations. So other things we generally used to see in the classroom textbooks, but this particular is still missing in the academia bridging. Okay? And one more thing we can see, second, this is nearly in our region, Kochi, just 22 days before, which I have taken from our public domain. You can see PCB design engineer, and again, you see they have clearly mentioned we should have proficiency in the IPC standard. So with this workshop, we are going to have three IPC standard minimum basics before you complete your degree. One is tolerancing and dimensioning, and then printed board circuits, and then high frequency circuits. And if time permits, I will go for 610 also. So these are three IP stand more than enough for entry level student. Okay, so I just want to show where the IPC stands in the job market also. Now let us come to our topic, IPC 261, printed board circuits. Okay, so what is the objective of the standard? So the objective of the standard is to establish accepted principle and practices for the dimensioning and tolerancing for the end products requirements, especially for PCB and PCB board assemblies. And as I mentioned earlier, this particular code is derived from ASME 14.5 M 1994 base. And now revised version also come, and some of the contents have been removed and some additional has also come, but we will stick to our basic code ASME 14.5 M 1994. And for this we should also have some sort of basic knowledge on basic terms which we can generally see in some other codes like IPC 50 and 310 to 220. These things are required when we go into depth. So today's our objective is to introduce what is this code means and what is the background required for this particular code. And most of the codes which you can see is closely related to ASME, so we need to rush up our basics from first year engineering graphics, and then basic mechanical engineering fundamentals, and then machine drawing fundamentals. And unfortunately the machine drawing has not been dealt in the electronics and electrical engineering curricula, but in mechanical they have covered, but they have only one topic called geometry dimensioning and tolerancing. So that particular thing also I will just refresh you so that you will feel very happy when you go for IPC 2615 code course. Now, if you go into depth, this particular course, what are the, standard? This I have given a screenshot of that table of contents. You can see what the code contains. It contains basic definition terms, for example, what is the actual size of the board and components, how to represent a basic dimension, and what do you mean by tolerance, and how to define unilateral tolerance, bilateral triangle tolerance, and what is the datum, what is datum feature, and so on. See, some of the important definitions have been come, but fortunately, this is also available in your nearby departments, mechanical and production electrical, and but unfortunately this bridging is not there. So I just want to enforce this particular topic. They have been already covered, so when you get time, please go to library and reference these particular fundamentals which is available in the mechanical textbook and electrical textbooks. But since it is very much important for our IPC 2615, especially for printed circuit board. And if you see general rules, and we have a datum referencing how to represent a component placed on the board. Okay. Now let us define what do you mean by geometric dimensioning and tolerancing. So it is a symbolic language actually, how to represent a schematic or diagram which can be universally acceptable without pen and paper. Okay, much confusion. And also we can generate using two-dimensional models very nicely, and we can utilize very standard parameters to notify or show some of the constraints given on that particular board. So if you see the diagram, we have a component here, and this component is kept on a base, and this base is referenced, some of the reference, and this kind of dimensionality and rules of dimensionality which we have already done in the first year, the similar thing will be coming again with some sort of different standard level. Okay, so these dimensions already we have done in the first year engineering graphics. You can see again we are using these things for our PCB design also. In addition to that, we do have some sort of different parameters notification. If you see some triangle in some 5.63 is given, this is nothing but diameter. And then now I have given some a table, a notification, and you can find different symbols are there. Each symbol denotes some meaning here. Okay, right? So those things we are going to study, what for A and what for this M rounded and 5 is given, and this particular symbol what for this. So all those things is having a particular meaning. This is what we are going to cover in this 1.5 lecture. Okay, so this representation By seeing this representation, one should easily understand or communicate the intended meaning of the component. That is the internal gust of this. Okay. So it's something but a symbolic language which is used in the PCB drawings, design drawings. And what it does actually, it is relates the functionality of the component. Okay. And we can see because of this GD&T, you will have more advantages and standardization. Why should we use this dimensioning and tolerancing? What is it necessary? If you have interchangeability, what do you mean by interchangeability? A component that designed and represented should be or manufactured should be acceptable by another manufacturer or designer. So here you have a small hole drilled. The same drilled hole should accept another component which is with the given diametral tolerance. Okay. So if it is not fitting, then there is no interchangeability. So accordingly, suppose if you want a M10 net, 10 mm a metric nut is given, and you have 10 bolt. Both should have fittingness. Otherwise, if there is no fittingness, then you have rejection nature. So in order to have that kind of interchangeability or usability, you are going to provide some sort of allowances. So okay, that allowance also we are going to see today. So that is the need. And when a datum reference is desirable, what is a datum reference? Suppose you are keeping a component in datum plane. Assume that we have a Cartesian coordinate system, the bottom plane, side plane, and right side plane. Okay, and bottom plane, assume that base plane. Suppose you are keeping base plane A, and how much distance from the left side plane and right side plane, how much distance you have to keep, or left edge, right edge. So this phenomenon is called as datum referencing. Okay, so when this is necessary, and you must have some sort of tool to denote the positional dimensions of the particular component. So that is where we require this GD and T. And because of this particular tools availability, we can go for seamless production because everything has been given, intended usage tolerance has been given, and it can be easily understood by the manufacturers. Okay, and thereby we are reducing the cost, and also use a uniformity, and there is no inconvenience in reading the drawings because everything has been given crystal clearly. And this is very important thing. We have to ensure the interchangeability of the mating parts at the assembly. So that is why we go for some sort of standardization, then is that geometry dimensioning and tolerancing. Okay. And these are some of the advantages again. With these very important things, numerous nodes has been removed. You need not write a lot of notes. Just you mention some symbol, that is more than sufficient. It is understood by universally. So this is a major advantage of this. It replaces numerous nodes, and you need not write paragraphs on. Just mention one symbol, it clears all. And also it offers better clarity and improved fitness and better inspection methods also. Okay. And when you have better inspection method or real tolerance, you will have less number of components rejected, and thereby you are improving the standards. Now let us see some of the terms or terminologies which is required to understand the code IPC 2615. The printed circuit board dimensioning tolerancing. What do you mean by this? The definitions is given in the IPC code. Dimension. Dimension is nothing but a geometric characteristic of a size which is specified in length or angle or location. Okay, it's a characteristic, geometric characteristic dimension. Then what is a tolerance? Tolerance is a dimension which is a total permissible variation in its size. How much permissible variation, plus or minus, okay, which is equal to difference between two limits of size. So that particular term is known as tolerance. So we have unilateral tolerance and bilateral tolerance. Okay. Now with this diagram, we can further understand how the dimensions of part and how the tolerance has been mentioned here. And if you see the left side figure, you have a small cylindrical part, and the cylindrical part you have two holes. So why I'm saying cylindrical part, they are given diameter. Okay, if diameter is not being given, then you can also consider as a small plate also. Now diameter is given, how the diameter has been mentioned here, and the hole size is given, and you can see from this particular location to this particular location, they have mentioned how much distance is required. The parameters have been given, and this from this hole to this hole, how much distance, that of center distance is given, and total length is given. So these are dimensioning a part with the appropriate analogy. And if you want to have this chamber, how much angle you want chamfer, so that dimension is given. Now if you come to tolerance, now how much tolerance is required, you have, for example, if you observe this particular hole, you have two holes in this, 2 into 0.375, and if you mentioned, they have mentioned two different terms, one is plus 0.005 and another is minus 00. So you can have positive of 0.00, you can have 0.005 extra material, okay, but you cannot have minus. So that is a unilateral tolerance, only one way they have given. Okay, so this denotes your variance. The next, different sizes of mating of parts. Suppose you have a PCB board internal hole via, we used to call via in case of PCB board. In case of production or mechanical, this comes as hole, directly we call part hole. Suppose if you have a board or plate, the cross section denotes the cut section. Okay, so we have made a cross. So this is the internal part, and internal part, as this is a maximum size of the hole, maximum size, and it also has some minimum size. Minimum size with respect to the allowance we have given. You can see this is the allowance. So the maximum size and minimum size, the difference we can denote as tolerance. So this much tolerance can be accommodated with this particular internal part. And if you see the external part, the maximum size is this one, maximum size or design size. Suppose you are inserting a rectangular or cylindrical part here. This is a design size, and the tolerance here is minimum size of this shaft and then maximum size of the shaft. This is allowable value which they have given. Like previous slide, we have given the maximum size it can accommodate is this one plus 0.005, and there is no minimum is 0.375 only. So this is generalized terms which we use for understanding the tolerance. So maximum size minus minimum size, minimum allowable size will give you the tolerance value. Now the deviations, the difference between basic size and the maximum minimum size called upper and lower deviation. So once we already seen plus 0.005 is upper tolerance, and if you have a minus 0.005, that is called a lower deviations. So now in this case, you can see two deviations very clearly mentioned. We have a component size, it can be 3.00 plus or minus 0.02 O2. Okay, now what does that mean? It can have the component, it can accommodate, this shaft can be accommodated even if 3.02, okay, or 2.98. So likewise, both side tolerance can be mentioned, that is upper limit and lower limit, upper deviation or lower deviation. Similarly, if you observe, this is the basic size of the whole, the component is a zero point 0.5 basic size, or we can use to say a zero line. In this zero line, it's nothing but you assume that is a small PCB board you have taken and you have drilled a hole. You have drilled a hole for how much? 0.5 you have a hole, design hole. But sometimes you can extend up to 0.001 also. Okay, it should accommodate. That is called allowance we have given, right? So that is how we provide upper deviation and lower deviation in the components and boards. Next, there are certain methodology available with respect to IPC 2615 printed circuit board. So the basic, apart from terminology, we should know how to dimension the PCB design. Okay, right now I have given very basic things. When you go for code, you will have the starting itself. You will have find a lot of terminologies, like we have seen the previous figure. Lot of modifiers will be there, and dimensionality will be there. So don't get confused. Just follow our today's class, and you will come to know at the end. You can easily read the uh, 2615 code. Now, in this dimension types of dimensioning, IPC 2615 gives two different dimensioning methodology. One is millimeter dimensioning methodology and decimal inch methodology. The simple difference you can observe very clearly. The minimum dimension in case of millimeter dimensioning starts with 0.90, whereas inch dimensioning you will have without zero it will start. So just by seeing this knowledge, we can initially observe which is inch dimensioning or it's a millimeter dimensioning. And mostly the dimensioning also will contain this particular logo IPC 2615 and that particular dimensioning type A02. So that also we should note. And in this case, if you find with how they are mentioned. So for example, 19.3 mm they are mentioned as we do in the first year drawing. Even for circle, there is no deviation, the same methodology only. Okay, and but please mention check the distance between the arrows. So that's very important. The arrow mark is very important. So there are two dimensions. One is millimeter dimensioning and inch dimensioning. The simple logic is inch dimensioning will starts without zero. So there is no confusion in this millimeter dimensioning. So most of the board nowadays comes with the millimeter dimensioning only. And again, some of the dimensioning methodology which is given by the IPC 2615, especially for PCB. Just observe. For example, we have a board here from edge to the corner, how to define the dimension and how to angle. So this is a generalized methodology, and there should not be any sort of overlapping and should be uniform. For example, if you want to mention this height and width, and the height also is given, and but this distance is not given to you. The angular distance is not given. Instead of that, they have mentioned the angular degree, 30 degree they have mentioned as far as this particular board is concerned. And we have a hole, and the hole position also very clearly mentioned without any sort of overlapping between the dimensions. One dimension is a pure dimension 28 they have given, and another dimension is the positional dimension of the particular hole from this edge to this edge. Now, since this is a simple component, we are directly going for 14 and 20, because from this edge it is 14 and from this edge, right edge, it is 20. Suppose a complicated part, we cannot say we cannot dimension like this. We need some sort of other tools to denote that the distance the whole from this edge is this much, and from this edge is this much, and from this angular distance this center point is different. So that is where we come for another tools which we are going to see slowly. So there we may require some other arrangements to denote this particular is located from these 3 points. Okay, so this is a very simple concept of representing a component or board with a hole. Okay, and width has been given, and there is no overlap between any dimensions. Please note there is no overlap. The next figure, how to grouping the dimensions. Suppose the board has different cuttings, and you can see the dimensions should be uniform. It should not be ununiform, downwards or overlapping the board and so on. It should be neatly and sequentially mentioned. And spacing is very important. As per this IPC 2615 code, the spacing is given like first major dimension should be 10, minimum 10, and the minimum 10, and then second dimension it should be minimum of 6, and there must be a gap which should be a visible. We please note this is a component and you have a line, and during our engineering graphics classes we generally miss this particular though it has been stipulated, generally we used to miss sometimes. But here, there must be a gap between the component and then tracing lines. This lines means lines. Okay, so this visible gap should be there. That we should note very clearly. And overlapping, which I already mentioned. And then if you have very high number of projections or representation, different holes and staggered holes and so in that cases we should have a very neat representation, and should not be a straight line like we mentioned in sequence. It should be mentioned uniformly, offset, uniform offset should be. So 14 is there, and then second offset is given, a right offset, left offset, and so on. So easily we can find out which whole, which dimension belongs to which particular. So this avoids the oversight issues. So this, even a simple dimension IPC 265 gives this much accurate regulations. So this is how we increases our ease, okay, increase the easy understanding of the drawings. Then next one, how to minimize the leaders which we provide. Suppose if you have 6 holes, you need not write all the dimensions. Generally, we do have done in engineering graphics, but still I'm just repeating with respect to IPC 2615. You find we have a 3 holes of 8.8 units diameter, and how they have indicated, we have only one they have indicated, and they are given a marking Y. So this Y hole has 3 numbers, 1, 2, 3. What is the diameter? They are given the diameter itself. And how to measure, how to mention the radius, board radius. If you find this, you can mention as radius R14, and if it's a corner, you must produce a leader here and then write straightforward R, or you can use internal arrow also. And if it's a very big one, you just make a sample and R130. Even affiliate. This also applies for the unlocated center also. Different radius which you mentioned. So this is a simple PCB board drilled hole, through hole. Okay, through hole we have mentioned here. So one single full wire. Okay, and this diameter is 12, and they have mentioned through. That means nothing but full wire, a through hole, complete hole has been mentioned there. Okay, and if it is only a few dimension depth, so then the dimension will be given here 8 mm up to 16 unit depth. So if you find this particular, the whole hole is given only for 16 units. Okay. So this particular is also covers exactly IPC 2615A and 28. This looks very simple, but unless otherwise you standardize your reading with even a single one, simple this content, it will not help you later. So we must be very careful in understanding the basics of this. And if you see the actual PCB drawing, it includes flucials. Flucials nothing but a marking which is given in the printed circuit board, logo marking and so on. So now it is a simple board they are given. In this simple board, you see, just see what, how many dimensions they are given. The center point they have mentioned 3xx, 3y dimensions, and from this mark, and this whole, the center point of this hole is given indifferently. You can find some of the different components has been given. So to different references they are given and different conditions also they have been given. So this is the thing which you are going to concentrate more. This particular example is for locating a circuit pattern using fiduciary relative or a plated through holes. Some copper linings also been given. This is apart from your regular circuit design. This is purely based on the mechanical part and mechanical dimensionality, not the circuit dimensionality. Okay. And these are some of the basic terms which one should understand before we go for 2615 application. What is the actual size of the component? How to define the basic dimension? What is tolerance, unilateral tolerance, bilateral tolerance, cumulative tolerance, and how to represent a simple datum. Datum is nothing but a Cartesian system in which you are keeping a component and you are defining with respect to three planes, and how to define the datum in geometrical way, that is called geometry feature. What is feature? Fortune feature is nothing but engineering component definition, and how much feature dash size, and fiducial silk mark of a PCB, and geometric tolerance, different types of geometric tolerances, whether it's a cylindrical, whether it's a plane, it's a parallel, and so on. And what do you mean by least material condition, maximum material condition? This too is very important as far as a PCB design is concerned. Very often you will encounter LMC and MMC in the PCB drawing, and regardless of feature, size, and virtual conditions. So these are a very limited number of terms I have mentioned in this PPT. You can have more than 80 terms and definitions in IPC 2615. I have taken a very limited one, which is very much closely related to your engineering fundamental, which you have been gone through in first years and second years. So that is I have taken only few so that you can avoid the confusions in future science. What is the basic dimension? Basic dimension, for you take a simple resistor hole or even simple what do you call it, capacitors. Okay, the dimension is given to you. It's a numerical value which theoretically describes the size and orientation. Okay, right. And what is a datum? Datum is nothing but it's a theoretical exact point or plane. For example, you can see that this is a Cartesian system we have given. In this Cartesian system, the hole is placed. Now, this hole is placed where? Upon which plane it is kept. So, representation of this particular plane is known as datum referencing. So, datum is nothing but the origin on which the compound is located. Okay. So this I have mentioned here, a datum is the origin from which the location or geometric characteristics of features of a part are established. So here in this case, establishment can be like this. It is resting on the plane 1, primary datum, primary plane, datum plane, and it starts with the secondary datum. And the intersection of the three secondary datum and third datum is its datum axis. So likewise, we can mention the center point of this particular hole. So that is called as datum referencing. So datum is clear and basic dimension is clear. Basic dimension already we have seen in case of matter. Okay. So three plane concept are just we have seen. We have three different primary plane, secondary plane, and to add to further how we used to define the primary datum. This primary bottom plane is given, and a compound is resting on that. So this is a primary datum plane, and secondary, and each one has some sort of regulation. For primary datum plane, how many contact points are allowed, similarly for secondary plane and third plane. And if when we refer to 615, they have exactly given the primary datum means you should have 2, 3, 4, 6. So when we go for designing, we should remind this particular point. Primary datum, and then secondary datum you can find is 90 degree to the primary datum. That's very important. and then tertiary, third plane, third data plane. And again, third data plane also 90 degree to the primary datum. And what is a datum feature? Datum feature is an actual feature on a part which is used to establish the datum. And what is feature? Feature is a physical portion of a part. It may be a hole, it may be a cut, it may be a slot, or it may be a flat surface, it may be a projection, or it may be a ribs. Sometimes external features. And feature size, how do you define feature size? Feature size with the uh, linear dimension and hole with the diameter and so on. If it is angular, you mention angular symbol. Okay. And the very important part, what do you mean by least material condition and maximum material condition? It's nothing but the feature of a size is the least amount of material within the stated limits. Now, if you observe this particular diagram, the diameter of the shaft is given. How much they are given? Basic dimension 0.255. Now, what type of dimension they are mentioned? Is it metric dimensioning or inch dimensioning? Just by seeing, we can say it is an inch type dimensioning. Okay, that starts lower and starts from 0.245 and so. So now, in this tolerance, how much they have given? They have given plus or minus 0.05. So now, in this case, the least amount of shaft diameter also given, or maximum hole diameter also we can take. So least material condition of a feature is the least amount of material within the stated limits, very least amount of material. Similarly, when we go for maximum material condition, we must take the maximum amount of the material which is being stated. Okay. Otherwise, we can say like this: the maximum shaft diameter or minimum hole diameter. And here, minimum shaft diameter or maximum hole diameter. Okay. So this is the very important part of terms: least material condition and maximum material condition. Then we do have some of the important part, uh, true position, virtual condition, and regardless of feature condition. The true position is the theoretically exact location of a feature. Okay? And there are certain tolerance zones are located at these true positions that we are going to see in the diagrams, which is true position, virtual position also. Virtual condition of a feature specified at MMC is a constant boundary generated by a collective effects of the maximum material condition limit size of a feature. Okay, so virtual condition generally exist in the MMC limit, maximum material condition limit, mostly. And regardless features of size. What do you mean regardless features? This is used to indicate a geometric tolerance or datum reference at any increment of size of a feature within the size tolerance. So we take the geometry tolerance or datum reference and apply any increment size of the feature from or within its size of the tolerance. Okay, and generally it is very strictly used, and it greatly affects the parts function. Okay, right. And there are some more tolerance symbols which we should know. And when we mention the straight lines, the symbol which we use is this one, symbol, straight line, and the flatness, and circularity, and cylinder. So these four symbols. Yeah. Shall I continue, sir? Yes, ma'am. Fine. The types of tolerance, form tolerance. You have four different types of form tolerance: straightness, flatness, circularity, cylinderity. And these four refers to the individual datum references. And then we have a profile reference, profile tolerance. It may be related to individual or related. I mean, different components, different references also. One is profile of a line, how to draw a profile of a line, and how to project or show the profile of a surface. These two symbols is used. Then orientation, location, and a runout. So these are things, some of the things we are going to cover today. And when you go for the symbols or tolerance reading, you will find this kind of symbols. You will mention only circle, and then you will have small modifiers and so on. Okay? And some last diagram we have seen something like this zero and marking. So that's nothing but a location or position of that particular code. So this is related to some other referencing. So that is why we have given orientation, location, runout. So these three type of tolerance is related with the other reference, other datum references. Whereas the form is individual reference, and this profile, it may be individual or sometimes it may also related. So this four is very important: form tolerance, profile tolerance, orientation tolerance, and location tolerance, and runout tolerance. This is with reference to your 2615. Different diagrams, I mean symbols have been given, and one should be very clear with these basic symbols to understand the PCB drawings. So when we have a triangle like this and a projection and A, that is nothing but a datum feature. Okay, and if we have a circle and line, horizontal line, it's a datum target. And what is MMC? Maximum material condition is M. Similarly, L, least material condition is L. And regardless feature size is S. Similarly, you can see a target point, cylindricity, circularity. We are going to see what is this difference between cylindricity and circularity. Okay. And even parallelism, some of the few terms which I will explain, and rest of things you please refer 2615 code, which is commonly available with the IPC website, or PDFs with some uh, even PCB manufacturers also. And a very important thing, perpendicularity, angularity, runouts, okay, and other symbols, countersunk, event, and slope, etc. And this is a very important part: future controlled frame. Future controlled frame. This is where we have seen the first drawing. Some of the position they have mentioned, some they have mentioned A, B, C, and so on. So this particular future control frame we will use to define the exact reference of that particular hole or a point on which the compound is getting placed. So this is a brief of your common tolerance symbols with reference to form, profile, orientation, location, and runout. So this is the future control frame. And when we see the very first diagram, we have observed this particular table. And now you can go one by one. The first part denotes the geometric characteristics symbol. Okay. So what is this particular symbol? We can easily go and check it with this particular symbols. This is nothing but a position. The next one is a commonly standardized symbol, diameter symbol, and then there is a tolerance value they are given 0.02 O2 tolerance, and then they have mentioned some modifier. This modifier is nothing but is a condition of the material or the datum point. And then they have three different segments, A, B, C. So these three exclusively given for datum references. So this covers your feature control frame. So just refer your previous diagram, and then you can easily understand the feature reference frame. Diameter symbol, and then position symbol, then diameter, tolerance, modifier, conditions of the component, location, and free references. And you can see again the same thing I mentioned with reference to one particular value. Okay, and here you see three dimensions they are given. primary reference, secondary reference, tertiary reference. Even sometimes the reference also has some sort of modifier. That is why we have shown one particular symbol, same symbol I have used, because there exists some sort of condition modifier. So that is why we have mentioned two modifiers. And this modifier is nothing but material condition modifiers. And now we'll go for one by one. What is straightness? How do you define the straightness of the component? Okay. So generally in a laboratory or industry, we use some sort of a profilometer to understand the straightness, or even optical methodology to understand the straightness and symmetrical and so on. And if you see the shaft, you see the dimension variation exists with the straight. Okay, and so that value we have mentioned in this particular component, the straightness is variation is 0.1. This is a symbol used for straightness variation. And if you see this, again, lot of variations are there. The variation lies within the 0.02 value. So just mention a simple line, because the line denotes to straight line. This is straightness. Yes, this is a straightness symbol, and we use straightness symbol, and then we mention the variation. So again, some advanced concepts. We have mentioned the shaft. This is a diameter we are given, and then two dimensions, upper limit, lower limit has been given, and this is nothing but geometrical tolerances. So this particular lecture, we are not going to touch more on this geometrical tolerance. We are concerned positional tolerance alone. Okay? Position tolerance, and some of the geometric tolerance is covered, but this is exclusively for hole and shaft. Okay, and this H denotes your hole size, and this 11 denotes fitness of the components, which is not required right now. This is exclusively for mechanical components. And we are concerned about this symbol representation, the symbol straightness, and then how much variations are there in the diameter. Okay. So again, the straightness axis. Now you can see how to measure this straightness in a laboratory. You can use a V block and use a dial gauge and measure it. Okay. And then that measurement variations you just note down and mention in the drawing. Straight line and 0.02. If there is a modified available, just check the modifier and just mention it. Again, the similarly flat size. How do you represent the flat size? This is a simple user, flat size, and again you have to measure the difference on the surface. Okay, 2 seconds. Difference of the surface, and then mention how much difference you observed. 0.2 with respect to this particular area. Now in this case, how do you measure the flatness? This particular, use the same dial gauge and measure the points. Okay, and mention take the average and mention the flatness value here. The on point surface must be between 2 points. That's very important. Okay. Similarly, what is circularity? How do you measure circularity, and how do you mention it? You mention a simple circle with 0.025. Okay. So how do you measure? Use the same dial gauge. This is the part given and the precision symbol, and just slide so once again, and then find out the variations in the circular size, and use the circularity symbol and mention the value in the PCB drawing. Then cylindricity in the linear side. So this is the symbol used for cylindricity. You have two slashed lines and then sheared lines and one circular. So this means this symbol directly denotes your cylindricity. So how much variations now? 0.25 variation in the component in its intensity. Now, this is the methodology how to measure it. Then again, there is some measurement symbols are given how to measure this intensity. So here if you see, by constraining part on axis and just rotate it around the height gauge or even dial gauge and record the variations. Okay. So this particular equipment is available in the instrumentation lab. You can also try and you can learn how to understand, measure the circularity and cylindricity used for these simple components. Okay. It's not a big deal. And let us go for next one, surface representation. How do you represent a simple surface as per IPC 2615? In this case is a curved surface. From curved surface, what is the generalized procedure? So we have already understood this is nothing but datum reference. This is a datum plane. We have already mentioned that it has some arrow here, datum reference, and this is the plane we have chosen. And from this datum referencing, what is the values? Now see, uniformly distributed, and this is sequence, and here uniform offset value they are given. It's not the same line, just offset value. And they have also mentioned the tolerance values, okay, plus or minus unit tolerance value they have mentioned. And now let us come here. This is what the future control frame, and the future control frame contains the symbol first. This symbol denotes your profile surface and how much variations, and then we have three references, A, B, C, three references we have. This is a reference A, and this is a reference B, and this is a top is reference C. So three references they have given. So with reference to this, we have to correlate the values. Then again, let us go for another symbols. What is angularity, perpendicularity, and parallelism? So the angularity symbol is this one, as we mentioned in your graphics, angle symbol and the deviations and the free reference or single reference. This B denotes your datum referencing. From this datum referencing, how much deviations we have, that we have to denote. So suppose you are denoting from a reference A, then how much deviations. So for example, if you observe here from B, what is the angle? This one. And from it's a parallel point from parallel with respect to datum reference A. Okay. So again, there's an angle mentioned in the component. So the angular measurement has been given, okay, and tolerance is given here, and then it's from your datum reference A. Okay. Then perpendicularity. The perpendicularity, first we should know the symbol and datum. You just mentioned the datum. This is the datum point or datum reference A you have chosen. From then again you just mentioned the perpendicular symbol for this particular component. From this reference, the perpendicular, and the tolerance is 0.12. They are from the measurement. You can see the possible tolerance which is obtained here. So much tolerance we have. So that value we mention it. So this covers your perpendicularity symbols. Then again, parallel. For example, from this surface we require to mention, and we require a datum surface. We have mentioned a datum surface from this datum plane or datum surface. You have already obtained the tolerance zone. The tolerance zone covers by 0.12, and hence this particular surface is a parallel to this datum plane, and it contains the tolerance. So this much variations, within the variations you can accommodate the component. Okay. So that is the greatness in this. By even the surface, top surface, you are allowing some sort of possible orientation. deviations. Okay. Similarly, when you have this particular two holes reference, you just observe from this reference how much deviations you're going to have. Okay. Because this is nothing but access you are giving. For even for access, what is the allowance you are going to give? So that has been mentioned in this. Okay. And how do you measure parallelism? Just use the same dial gauge, use full movements, and take the values and represent in the modifiers parallel, and you have deviations of 0.02 with reference k. Then we have another two terms, circular runout and runout, total runout. So circular runout is nothing but the deviations in the part when we get rotated. Okay. So here we have mentioned circular runout, single arrow we used to mention. So how much deviations you observed, we just observe and take the value with the unilateral tolerance or bilateral tolerance, and the reference plane here is A reference plane, and from for A reference plane, the deviation which you already observed using your dial gauge, that has to be mentioned here. Similarly for total runout only difference is you will be having two error mark. Okay, so total runs control the entire length between two imaginary circles. So we'll be going to measure between two circles. Okay, and this covers your different symbols used in the 2615. Okay, and we do have two generalized rules in 2615. The rule 1 states that where only tolerance size is specified, the limits of size of an individual feature size prescribe the extent to which variations in its geometric form are allowed. That means the limit size which is given into the feature size, okay, with the variations only we can use. If there is without variation, we are not supposed to go forward, because if without variations, if you go, there will not be any sort of interchangeability. And then no element of features shall go beyond the maximum material condition boundary of perfect form. So this is another very important point to be considered. No element of feature shall go beyond the maximum material conditions. Okay, and the form tolerance increases as the actual size of the feature departs from the MMC towards LMC. So there should not be there is no perfect form in this boundary requirement in case of LMCs. So better with respect to boundary requirement. Now let us briefly understand what we mean by rule 1. You take a shaft and with a diameter of 5 unit. This is a 5 diameter symbol, 5 unit you have taken, and the deviations are maximum deviations given 0.405 point. So if this is the condition given, then we have a maximum material condition is at 5.040. Okay, now we assume that this part is produced at 5.04. Then according to rule 1, the part should be in a perfect form. Okay, in this form, because we have given the maximum material condition. Okay, and you should have a perfect straightness and circularity and cylindricity. Okay, so that is the simple meaning of the rule 1. Okay, maximum conditions we have gone, and then rule 2 states that the regardless of feature size automatically applies in a feature control frame to individual tolerance of size features and to datum size features. That means the MMC, maximum material condition and least material condition, must be specified when these conditions are required. We should not leave this MMC and LMC, because that is very important when it comes for material representations. Okay. Then we'll go for, yeah, simple analogy to understand the rule 2. Here we have a stepped shaft One is with 5 units diameter, another is 5 or 3 units to 3.004. Okay, so these are the variations are given. So the bigger diameter assigned as a datum now, this one, and the second diameter 3 is controlled by a concentric diameter tolerance, and this tolerance is applied without any dimensional size constraint. Okay, so because we go for least metal condition here, and hence this particular dimension is mentioned as RFS regardless of feature size. Okay, now let us go for a simple data referencing revision, which already we have gone for. So three planes we have. Primary datum plane. When you have a component resting over here, we take three reference planes: base plane and side two reference plane, secondary plane and tertiary plane. Each plane is 90 degree to each other. Some printing mistakes there. Positioned exactly 90 degree to each other. So this is called datum referencing plane. It's very important for all sorts of basic understanding of our PCB design, positional tolerance and dimension tolerances. So primary datum, it provides a functional relationship, and the secondary datums are produced perpendicular to the primary datum. So the measurements can be referenced from the uh, first primary and secondary. Then tertiary datum is always perpendicular to both primary and second datum. This is already mentioned, each should be 90 degree to each other. And this is the datum reference frames. We have a primary datum here, and we have a second datum, we have a tertiary datum, each 90 degree each other. Okay. Now some of the examples we have mentioned here. The first datum plane, this is a component resting on the first datum. Okay. And if you see this particular, what is the degrees of freedom? What is the degrees of freedom means? What this component, the ability of the component to move with other axes. Okay. Now, if you observe the Cartesian coordinate system, sub-Cartesian coordinate system, x, x, y, z, okay, and u, v, and it's nothing but you can see it can rotate. This particular component can rotate about which axis? It cannot rotate about which axis? It can go in the translative, because bottom it cannot go. It can go only positive direction. Okay. Similarly, it can go in the xy. It cannot rotate and rotate in this direction, constrained, and it cannot rotate opposite direction also. It is constrained. So likewise, each rotation constraints we should note with respect to each datum plane. So when you go for three datum plane, you will find the constraints available. Okay. And if you find here, what's the constraints here? It can move only one direction only, on positive directions, not in negative direction. And these directions arrested, and back direction is also positive direction is allowed. So one translation is in Y is given. Okay, and similarly, the datum referencing from with reference to the frames this mentioned here, position mentioned, and diameter and so on. Okay. This is again one example for the position tolerance of this component. Okay. And again, this is again a very important point in this to be noted. How do we represent the data features, the secondary planes? And if you see the diagram very neatly, and they have given a board, and you have various component drilled holes are there, wires are there, and from this various mentioned, it's a perpendicular symbol, and from the B point, the B reference they are given, and from reference A, and they are already given the metal conditions and tolerance also mentioned here, plus or plus 0.1. Okay. Similarly, we have to understand the basics of representing the position as well as tolerances, and with need referencings from datum referencing. This is the objective of this particular lecture today. Okay. So again, one more locations I have given here. You can see there are two features is given. The datum feature simulator is given here, two features. How do you represent now? You take this as a datum, and a plane, you can have two planes, plane A, plane B, okay, and you can also have a plane axis also, okay. So this covers today's class, and tomorrow we can start with the generic standard on a printed board design. So with this, I'll stop today. So if any questions, if you want, you can ask right now. Though this kind of readings looks little bit tiring and you know very uh, tiresome, but these are all very basic things as an engineering student we should know at this beginning level itself. Once you complete degree, and it's very difficult to go back to your basics and again studying. So that is why I have taken only these particular topics, which is exclusively covers even your second year, third year level in the engineering. So you can go through this particular course once again, and learn the basics of these particular dimensions, and go to the lab of instrumentation lab, both applied electronics or mechanical. They have the dial gauge, so that you try to take one component and understand how to represent the circularity, cylindricity, and how to represent the frame. I mean, the circular frame. So you will have a first-hand experience rather than going to a company and then taking the vernier caliper or dial gauge and learning there. Being an electronics engineer, you use the adjacent lab, other department labs just given freely to you, and make use of this kind of fundamentals, because these things are inherently welded with your practical, as far as PCB design is concerned. So my recommendation is to take the IPC code and just reference, because you may be looking very differently. Why should we go for mechanical lab and study the basics of tolerance and so on, these concepts. Uh, to remind you back, this entire tolerance is derived from ASME 14.5. So that is closely related with this particular measurements. Okay, so better take a PDF copy of 261 IPC 2615 printer circuit board, and take the basics and go to the lab, and you do your own measurement and understand the datum features, and then what is the maximum metal condition, minimum metal condition, and you draw a simple diagram and mention the datum references with reference to IPC standard, not the ASME, because ASME will give you more elaborate on mechanical component thing, but we have to restrict ourselves with the printed circuit board alone. So, so this is my advice to the second year, third year students, so that will have very skilled experience before you leave the institute. So any questions with respect to IPC 2615 introduction? Panmani sir. So any questions now? since we have some time, I will just show the. Uh, I'll try to project the IPC code, which you can see in first hand. Let me try.
Participants, if you have any queries, please.
I will show the code once again. I'll try to come in presentation mode right now. Just few seconds.
Okay, sir.
Okay, fine. I'm unable to project the PDF. I can send it to your coordinator later stage. But if you have any specific query with respect to or understanding of the 2615, you can come in line now. Because this particular code is very much important as a PCB designer point of view. All other things you'll be learning, but this kind of codes are if you learn during your course itself, and by utilizing the allied department lab in first-hand experience if you have, then it will have a more skilled experience when you go for interviews. You can will have more strength to attempting the questions with respect to IPCs. If somebody asks you IPC 2615, what is that? You can easily brief. It's a printed circuit board tolerance. Now, what is the tolerance level, and what is the geometric tolerance? What is the symbols required, and how do you measure the symbols? So those things you will not be learning any textbooks unless otherwise you go to the lab. You take the code, and we have seen some of the symbols. For example, cylindricity, circular. What is the difference between cylindricity and circularity, and straightness? How do you measure it? So those things generally people used to leave. So that is where the gap exists. So unfortunately, if you refer very closely, these PCB IPC standard, if you just refer your just browse today evening a PCB IPC website, you will find the all the standards is given in very few languages. To surprise, of course, English is there. To surprise, most of the IPC standards has been translated into Chinese. Just imagine, more than 20 years before they have done it. And even now, that is why the penetration, the Chinese companies, most of the more than 60% of the PCB manufacturers are with them only. So that is the painful part for our industry, domestic industries. We design very straightforward, very simple circuits, even single sided or even double sided. Still, the multi-layer PCB design methodology is still lagging, still far way to go. So that is why even if you see most of the boards we import from abroad only. So I hope with this technical data, I think in your batch, if somebody comes forward and you as a team and develops an innovative methodology to fine tune the gap and produce our own boards. Of course, nowadays people have started a lot of PCB boards are coming, and high-end boards are flexible PCB boards also. Our people have started, but the progress rate compared to other countries is far away. The gap is very much away. So we must work very hard in a smart way, such a way that the gap can be reduced in the over the years to come. And a lot of technical background is there. So being a mechanical person, I have taken this initiative when I wondered when our own students is going for to other manufacturers and bringing the board, and people are not manufacturing themselves. So that is the motivation which I have shown the last class. The very second figure I have shown, it is been conducted in our Jodi campus itself. So you should feel proud and you should go faster rate, and you try to design at least double-sided PCB board in our lab before you leave the institution. you you have more facility in the institute, and to your knowledge, you have one more facility near Palakkad, where we have multi-layer PC board printing facility. You can take an permission through your IETE, and you can design and you can have one full day demonstration session to understand the multi-layer PCB design. So when you go there, if you go with a prepared or basic understanding of these IPC codes, so they'll be very happy to share more knowledge on this PCB design. That much I'm sure, because without understanding the basics of these industrial basics IPC codes, and if you go merely with some software is necessary, but the basic fundamental is also very much vital. So you go with the fundamental and ask the experts to explain, so you will have very much first hand fruits. So the floor is open to discussion. So I'll be very happy to get or clarify whatever I can share. Even if I don't know, I will talk to the experts and I will get you more insights on this topic, which is very much needed as far as electronics and communication is concerned.
Students, if you have any queries, please unmute and ask the question.
മലയാളത്തിൽ പറയുന്നു. Or you want me to ask like questions classroom? Arjun Saju లైన్లో ఉండో?
Alan, you asked something now. What's it? ALC PCB manufacturing. What is it, Alan?
Okay, anyhow, no issues. So I'm very happy to get all your queries. So when you go for PCB, when you take the PCB, double two two or even this 2615. So the very first thing when you see the diagrams, it's very complicated. So you will lose control or you will be tired. So don't worry. First, understand the very basic which I have shown today, and take a pen and paper and draw yourself. Understand what is cylindricity, straightforward, straightness, angularity, and go to the lab straight away to the instrumentation lab and get the tools in measurement. Just measure by yourself how to measure the cylindricity, circularity, and you will have more interest on that. So then you put it on that particular concept, you bring it to PCB design again. So you will understand. Of course, you will be getting very much thorough with the basic schematic ORCAD design or Algiagro, whatever software you're using. But the background, if you come to know, then you will have more strength to address the issue. If there is no question, then Parman sir, we can close. So tomorrow we will take two IPC codes, and I will touch the design for electromagnetic compatibility, and design for reliability, and design for thermal. So these three and one code I will cover. So with that, we'll close the workshop tomorrow. So if you have any questions with the last class, also you can mail to me. So my mail ID is already available with the organizer coordinators. So feel free to ask any questions. And remember, I'm not a big shot in the PC, but I'm a facility provider to the young students. So whatever I can do for your improvement or career improvement, I'll do my level best.
Okay. So no questions. We'll wind up the session. Okay. Thank you.
Okay, thank you.
Thank you, sir. Thank you.